Very good morning. My name is Roshan and I'm working with Guru Nepal and I'm serving as a managing director. And here we represent Earthbag technology. It sounds simple, Earthbag, but yes, as the way the sound is, the word is simple, the technology is too simple. So the people, like when we came to Nepal, it was like a challenge for us to convince the people because it was very new term for Nepalese people. But when we started and doing projects, when we went to the villages, we found that the student, especially the people, students, like engineering students, architects, they were like quite excited about the technology and they started like implementing it. And there was no trouble for us to implement this technology in remote Nepal and to help the real Nepal. So if we'll talk about the brief introduction, what is this technology about? This Earthbag technology is inexpensive, simple, sustainable method of building earthquake-resistant structures. We'll talk about the basics. It's earthquake and flood resistant, cost-effective, durable, easy to learn and build, and eco-friendly. Basically, with all this structural calculation, the test has already been done, and it has been proved that it's safe and strong enough, and it's cost-effective because when we'll just go to the budget analysis, we'll go in detail. But here, to build these structures, we use maximum local materials. It's like 56% of total materials are local, like gravel, sand, soil, and all these things. That's the reason it's cost effective, and the people who don't have enough funds, even they can rebuild their own houses using their local materials. And it's durable because all the structures which were built using this technology have lasted for hundreds of years. So it has hundreds of years of histories which came from military, and it's easy to learn because you don't need to be very much skilled to build these houses. Like whenever we did projects, we sent one technical supervisor and we hired the locals of villages, and they were like competent enough to build their own houses, and we could just set up an example in community. And it's eco-friendly because we are using local materials, natural materials, so there's no harm when we build these structures in villages, and there's no harm towards the environment. Earthbag buildings, we can also call it as reinforced rammed earth in a bag. So it's like this technology is very similar with rammed earth, but it's much more stronger than rammed earth because we have extra reinforcement and we put shell in a bag. So even bag, this polypropylene bag provide extra strength to the structure. And it's all about wall system where we use ordinary shell in polypropylene bag, and we use barbed wire which serves as a mortar. We don't use conventional technology, conventional materials like cement. It's very simple. Barbed wire can be we can find in the market, in the local market, because it's easy to find. The people are using for a fence, but here we are using as a mortar, and we have extra reinforcements like buttresses. We pin vertical rebars which goes all the way to the wall system, and bone beam on top of the wall system is mandatory, especially in seismic active zones, because it provides integrates the structure and forms a matrix using the barbed wire too. And the other USP of this technology is all about foundation. We are not using conventional foundation. It's double-tiered foundation which serves as a shock absorber. And like normal vernacular design, on top of it, we just have light roof. So we are not doing concrete roof or terraces, we are using timber as a roof truss, and you're using CGI, like simple seats, to cover it. We'll talk about technical feasibility. This is the other process we submitted to DUDBC to submit to publish in like catalog volume 2, So this is step, the production method and construction technology. These steps 1, 2, 3, 4, 5. We'll go in detail in other slides. But the first of all, what do? We send our supervisor to survey the site, and we just see whether the site is suitable to build earthbag structures or not. And we just test the soil. To test the soil, we don't have to send soil in lab. It's very simple. Like we always do the manual test, and we just see where the clay content in the soil. Like when the soil, then we have a soil property that is like we need 70 to 75% sand and 20 to 25 to 30% of clay. Like enough clay to bind the sand particles, and then we just see we level the site, and obviously leveling site is really important. Always important in any kind of structures. And then we dig the trench. You can see the rubble trench foundation is very different than the conventional foundation. We install trench drainage especially when the sites are on cliff, because we need to avoid water, keep the water away from the structures, because of course water is not good for any kind of structure. And we fill and place the first course of gravel bag on top of the rubble trench foundation, and we lay 2 strands of 4-point barbed wire on top of each course and add wall ties on each course, because we use wall tie to attach mesh. It helps to plaster, because when we do cement plaster, like the cement plaster doesn't attach with the polypropylene bag. So in that case, we're using mesh. And for mud plaster, it's not mandatory that mesh is not mandatory. We can just do mud plaster. It's simple to attach. But especially in remote Nepal, we have started using mesh, because they're suffering from, they're victim of rats. So, and of course, and they create holes in walls. In that case, we have started using mesh even if there is a mud plaster. And the 7th stage is we lay second or third gravel bag layer above the flow level, just to prevent it from water. And we are using, like, how do we attach, how do we place the gravel bags and the earth bag? We are using slider. So what do? When we just have one course of gravel bag or earth bag, so we don't fill bag and ground and lift it. We just do on wall, basically. So we are using metal slider on top of barbed wire. So while filling the bag, right, it doesn't get hooked in the barbed wire. And once it's filled, right, we lay the bag and slide the metal slider from there. We make door threshold, install door frames, and also door box, just like normal structures. Like whenever we do install doors and windows, we're using these sort of things, like a normal building. We prepare soil for earth bag, seed, maintain 10% moisture, which evaporates later. And we need 10% moisture because while tamping and we ram it, okay, we need to achieve highest compression. So, and this moisture provides extra compression while tamping the bag. So the other steps we'll go in detail in other slides. So we will talk about rubble trench foundation. So how do you do rubble trench foundation? So when we go to the site, we dig 3 feet deep, and it should be like 2 feet wider, the normal foundation. And we fill the trench, like we just with rubble up to 2.5 feet, like 2 feet 6 inches. And you can see here, there's a perforated part. This is a French drainage. So when we are on a cliff, we install this. because on cliff we always suffer from water when it's during the rainy season. If the site is not is on top of hill and the water cannot contain that, so it's not mandatory that we need to install fence drainage. So, and we are also using filter fabric. So we just fill the rubble up to 2.5 feet and just cover the entire rubble tent with filter fabric. And once it's covered, so we have first course of gravel bag underneath the ground level and 2 courses of gravel bag on top of it. And after that we start earth bags. And you can see here, all these bags are hooked and attached with barbed wire. So this is how we just do the rubble tent foundation. So you can see that the superstructure, the wall system, is not attached with the foundation, but it anchors because earth bag is heavy enough. So the massive weight of the structure anchors itself to the foundation. So we don't have specific attachment to the foundation, right? So the superstructure is independent. So during the shake, right, the superstructure moves independently. Okay. And we can see that these all are loose rubbles. So all these rubbles serves as a shock absorber. We don't put any concrete or cement to attach all these rubbles. It's loose itself. We need to protect the structure. We'll have to keep water away, so you can just do footing, concrete footing, or mud footing, especially on cliffs because the water can come here. But if we don't have cliffs, then we don't need all this footing and all. But of course, we just do footing just for look. This is the French drain. You can see here, all these are perforated. We created hole. And you can see the black thing is a filter fabric. So we just install the fence drainage and then just put loose rubble and we just cover it. The entire rubble tent with the filter fabric. Once it's covered, you can see that here are the gravel bags and 2 strands of barbed wire going all the way to the wall system. Okay? So we don't cut barbed wire. We only cut when it's needed. Okay? And it goes all the way to the wall system and forms a matrix. Okay? So this single wall, even if it's weak, it gets support from other walls. Okay? So it's not easy, the walls doesn't fall itself and becomes a single unit here. And we have just used bricks because it's heavy, the barbed wire, and it can uncoil. We have uncoiled it from the coil, right? So just to fix it, we have done it. And when we just lay another course, we use slider here on top, fill the gravel on top of it, and lay it, and just move the slider. Okay. And then it gets hooked to the barbed wire, the other course. Because you can see the continuous wall in corners. And here you can see the corner buttresses. So the example is, you can see here that the barbed wire has come here, goes from to the wall system somewhere, and then again it has come and gone through like this. So we don't cut it. We only cut when it's required. This is how we fill earth bag. You can see this is the slider, so that the bag won't get hooked here. And once it's filled, we close the bag and lay it. And to close, we're using galvanized wire. We're using galvanized wire, GI wire, and we can also use nylon thread and end it to do it. This is a model of slider. This is an angle just to how to move. And we need to have proper overlapping. And you can see in the wall system we have alternate layers of bags and barbed wire running bonds. So like a brick system, so you need to have overlapping. But we need like maximum overlapping. There's good workmanship, there's bad workmanship. So of course we don't expect such kind of wall system, right? So we need to ram it and will label and flatten. There are the corner options. See? So this corner buttresses is easy to do. Like you can see 3 different types of corners, but this is the one which is very simple to learn and do. Right? When you'll be using like corrugated steel, metal, it's like high cost and complicated for the villagers to learn. So it's easy, like in like all our projects we have used like corner buttresses. Two cylinders. And we're talking about vertical rebars which goes all the way to the wall system. So how do you do that? So when we just come to the seal level, the window level, we just spin rebar, okay? And then once it's pinned, and we go on top and again, we just pin rebar, okay? So while pinning rebar, the rebar should not be tacit. You need to have at least 1 feet of overlapping, right? You can see the 1 feet of overlapping. And the rebar, which is on the top, gets connected to the bond beam. So this is how the bond beam is attached to the wall system. Okay? So concrete bond beam is attached to the wall system here. This is reinforced concrete bond beam. And this is a plaster. You can see this is a mess. So we need mess if you're doing cement plaster. And you can see in other picture here, once it's like plaster, it looks like a normal house. So just to understand, this Earthbag technology is all about foundation and a wall system, right? So it doesn't like create like an impression that we're living in a very different house. Okay, the person who will be living can have the same feeling that I'm living in a similar house I was living. This is a truss roof design from the government. Like we're using that normal like roof design, the truss, the timber truss, from NBC, Nepal Building Group. This is 1-story Earthbag house in Gorkha. It was our first project that we did in Gorkha. This is the completed Earthbag house in Gorkha. So, like, if you see the normal houses, like you, of course, you might have experienced and seen like lots of Nepali houses. So how can you differentiate that this is an Earthbag house? Is there any way you can find that this is an Earthbag house? No, right? There's only one thing that can give you a signal that this is an Earthbag house. That is corner. You can see the corner buttresses. So we don't see buttresses in normal vernacular design. But here, we're using buttresses because we are in seismic active zone. When we do projects in India, we don't have buttresses there because they are not affected by earthquake, right? So we have just taken like extra precautions to like make it stronger. So we'll talk about the specification. We're talking about like how deep will be the foundation. So here you can see this 3 feet deep and 2 feet wider. So why we need 2 feet wide trends? The thickness of a wall is like 14 to 15 inches. So during the shake, it needs to have enough space to move, right? So here you can see that it should be in center. So during the shake, it can move independently. It will have enough space to move. So we let the structure to move during the shake. And you can see 2.5 feet of rubble, 0.5 feet of gravel bag below the grade, like underneath the ground level, and 1 feet above the ground level. And often constrained plumbing. So in like remote Nepal, like they don't do plumbings and all, but it can be done, the plumbing. So we need to plan it. So you can like treat this house as a normal house. You can have plumbing, you can have electrical wiring and all. So you can pre-plan everything. And even if you like to do it like in villages, they cook inside the house, right? So how will, and then we can just install the smokeless oven and all. I'll go to this slide of Kamala house. You can see on your left that there's a blue pipe coming out of the wall. Yes, that is smokeless oven. So once we installed it after completing the house, we thought of having like kitchen stove inside the house. So, and we drilled it, okay, to bring pipe into the house, and we installed the smokeless oven. So this is a perfect example that you can treat this house like a normal house. It's not like that you have built and you can't do anything with this structure. So this big Earthbag wall, so the height to thickness ratio will be like not more than 8. 2 strands of barbed wire between each every courses. Roof projection, the roof covering should project at least 2 feet around all the exterior walls. So during the rain, like we'll just have to protect the wall, like structure from the rain, right? Especially if it's the mud plaster, right? So even if you do like normal house and it's mud plaster, so it's like normal. You can see you can have like mud plaster or cement plaster. We'll talk about the openings. So minimum 3 feet from inside corners, minimum 3 feet between the openings, and maximum width of 5 feet. So if I have to explain here what is opening. So opening means like doors and windows, right? So from inside, you can see that if this is a corner, so you cannot have opening in the corner. You'll have to come 3 feet in center, to a center. Okay, you cannot have doors and windows in the corner. Minimum 3 feet between the openings. So if you have like the door and window on the same wall, you need to have a gap of at least 3 feet. And the maximum width of the opening should be 5 feet. So, like an example, that if you are installing a window, so it should not be wider than 5 feet. Is it clear? So then reinforcement. So we recommend buttresses in every corner and every 12 feet of unsupported wall. So if the wall is like 20 feet, we recommend that you need to have buttress in center somewhere, because the structure is flexible, right? So we recommend that you need to have a buttress, and you can see the example that we have like buttresses in the corner. So we need to pin rebar, so we have certain guidelines to pin rebar. So what do? We need to have rebar in every corner, and then we need to have rebar in every buttresses too. And in every opening, if this is a window here installed, so you need to have rebar going in every opening, corner of the opening, here in the corner, and if the wall is long enough, then you need to pin rebar every 3 feet distance. And it's individual rebar. We don't use concrete to fix it. It's very simple. And then we can have like timber bond beam or concrete bond beam. So timber, like sometimes if you have to buy timber, you need to buy good quality timber. Sometimes it's expensive. So it's better to use concrete bond beam. And it's easy to just attach to. And you can see it was like very feasible for us to implement, because when we invited Dr. Owen Geiger in Nepal like last September, like not to see during like September 2015, right? We just trained like nearly 1,000 Nepali, right? Since April, like so far we have this training. Like during Open Geiger, like we are doing training in like Tribhuvan, and he like himself trained like over 500 Nepali like architects, engineers, staffs, members, volunteers from different NGOs and RNGOs. And then we started training the Nepalese after during like December 2015, and so far like we trained like over 500 Nepali architects and engineers and the people from different NGOs and RNGOs. And we have also trained the people, the local people, because when we went to remote Nepal to rebuild, right, we didn't hire the experts. We are hiring the local people, and they have learned a lot, and now they are masters, basically. And you can see the 10 house concept. So what is it all about? Here, the people help people. Like, we went to Kauli and we showed. In Kauli, we are providing material and one technical supervisor to help them to train them. And here, they are helping the families. So you build my house, I'll build your house. So they are just saving extra cost of labor. Okay, and they are trading labor themselves. We have certain limitations too when we do Earthbag structures. So it's cool, it's easy, it's durable, it's cost effective. But at the same time, we have certain limitations. But it's very simple. So the first thing is, if the soil is soft or weak, we don't recommend that site. Right. And even like any kind of structure is not recommended if the soil is not suitable for the structure. And we also avoid the cliff and slope. So since Earthbag is a permanent and heavy structure, that's the reason we are like avoiding cliff, because it can cause landslide. So, and we have like other limitation, that is 1 story. But since it's heavy, the wall system, so we don't recommend 2 story. So we have like created these limitations. We can go like a little bit higher if there's not earthquake zones, but not in this seismic active zones like Nepal. These are structural calculations. So we have our engineer, he can explain to you the structural thing, Manish. So yeah, Manish.
Hello, I'm Manish. I'm an engineer working for Nepal. So these structural calculations are based on static method of seismic analysis. And basically we calculated calculated the strength of Earthbag structure in case of compression, in case of tensile strength, in case of shear strength, and in case of deflection from the force, that is called drift. So in case of compression, Earthbag structure has been proven really strong because of the polypropylene bag that surrounds the earth, that like it's kind of a membrane around the damped earth, so that provides tensile strength to the structure. The second one is shear strength. So basically, shear strength is provided in case of Earthbag structure by barbed, and we also pin the Earthbag wall with the vertical rebars that also adds to the shear strength of the wall. So while calculating shear strength, we incorporate the strength provided by barbed wire, the strength provided by rebars and plus the total resistance in between the bags, that is in between polypropylene bags. So these three are the components which provide shear strength to the earthbag structure, and we compare it to the total seismic force generated from an earthquake. So again, the total force generated by earthquake has been an earthquake structure can easily resist that forces. Next one is tensile stress. So basically, tensile stress is resisted by earthbag structure just because of its weight. So what we compare is total compressive stress at the bottom of the earthbag wall with the total tensile stress generated within the wall. So again, it has been found safe in case of tensile stress. The third one is deflection from the force. That is the total deflection of the wall at its top due to the force generated by the earthquake. Again, the total deflection is limited to 1/80th of the height of any earthbag, any earthen wall in fact. And again, the total deflection from the force of an earthquake has been found less than the allowable deflection as per the New Zealand code. So these were the total analysis of earthbag structure against earthquake forces. So and in every cases, the earthbag wall has been proven stronger to these forces. Thank you.
Thank you, Manish. Now, if we'll just focus on the cost. Cost has become a biggest factor to implement technology. Like there are various technologies in Nepal as alternative technology proposed to the government, and they're looking for any technology which can be suitable for the normal family, whether they can afford it or not. And when we had analysis, since we know that we are using maximum amount of local materials, so how can we define local? The first thing is that whether we just find the thing in country or nearby town, district, universities. So when we went to the list of the materials required, we had there the important materials: timber, bamboo, gravel, silk, sand, and recycled windows and roofs. They are the main ingredients to build earthbag structures, and all of them can be locally found. So you don't have to ship anything from India or import anything to build these structures. We don't need any kind of sophisticated machineries to build these structures. It's very manual. So, and the other thing which was important, when we did the budget analysis, we found like 86% of the entire cost stays in villas. Out of which 30% is a labor cost. Right? So it also provides extra employment opportunity to the locals. And it's more like labor intensive basically. And if we have to buy materials, it's only 14%, like barbed wire, bag, nails, galvanized wire, like CGI for the roof. So all the things are only 40% of total budget. So what are the subsidies the government is planning to provide to the family? So if we just consider the local materials, if you consider the labor, right? So the money is sufficient enough to build their own houses. So in that case, they don't have to be under the loan from the bank. And almost all of the materials are manufactured in Nepal, like bags and tubes, barbed wire, mats and all. So we have certain qualities. You can see that what kind of bags we are using. So as per our guideline, we are expecting like 80 grams per meter should be the weight of the PP bag. We can easily find such quality of bags. and in Nepal. And other materials, like whatever the materials are there, we can easily find here. And we talk about the cultural aspect of this technology. So it matches with our mission, because our mission is to develop and build structures with and alongside members of local community and in accordance with the community's needs and desires. So whenever we do project, we go to the village, even if it's remote Nepal, and we just have a meeting, a community meeting, and we have found that like culturally they have accepted this technology. Right? They don't find it like weird enough because they are attached to the soil, they are attached to the culture. So it's not like a prefab or other technologies that they have to bring other things from Kathmandu, whether it's suitable or not, because they have been using soil for their vernacular design forever, right? And they're much more concerned about looks, that how will it look after building. So here you can see on top, all these are traditional designs using like stone masonry or RCC or whatever. And when we build back structures, they are our designs. So there's no difference. It means like, so the structures like as per the design. So they can just have the same feeling of vernacular design. Here you can see, this is a 10 house concept, where like you can see that the normal female workers can build their own houses. To build these houses, we had only 2 male workers and 6 female workers who built this structure. So we can, in this case, we are also empowering women and providing jobs to them too. It's sustainable because it requires minimal amount of cement just for the bond beam. If they are looking for mud plaster, concrete, wood or steel. In this case, we have like reduced the transportation and fuel cost because we are using maximum local materials, and it's very fewer materials that we just bring it to village from Kathmandu or like urban Nepal. And this is how we're looking for Nepal in the future. If we'll start building back structures, this will be the look. Now, whether the structure is durable or not. So last time when we had like the question was there from professor that how long will it exist and what's the life of the structure? It's ridiculous, like because it's something theoretically it's like hundreds of years. Because what is the life of soil? It's like infinite something. And there was a test done by Federal Highway Administration in states before using this PP bag under the highway, especially the retaining walls in the highway, and they found the half-life of PP bags, PP fabric, could be 500 years or more if we will protect it from UV radiation. Okay. So we just get UV radiation from sunlight. So the concept is, if we just plaster the bag properly, this structure can last for hundreds of years. Like normally when we talk about cement, it's 50 years, theoretically people say it's 80 years, but in our case it's hundreds of years. So it's durable, you know. Thank you.
All right.